Hi everyone. In this video, we're going to talk about permutations and combinations, which are different methods of counting. So what I mean by counting is not like counting on your fingers, but like counting sets where the answers would be very large, such as how many license plates exist in the world, how many telephone numbers exist, how many different ID badges can we create at Stockton. So those kinds of problems where you are counting a very large number of things can be done systematically, and there's certain formulas that could be used to determine the answer. We're going to study 4 types of counting problems. We're going to talk about combinations when you're choosing elements from different sets. We're going to talk about permutations when repetitions are allowed, permutations when repetitions are not allowed, and combinations when you're choosing elements from the same set. So we're going to do an example of each of these kinds of problems. I'm not going to go through the formal mathematical formula that can be used to calculate these types of problems. I will briefly mention it to you, so if you're familiar with it, you're welcome to use it, but I won't go into detail explaining why they work, because I don't usually use them. Okay, so the first example is a combination problem from different sets. So let's say you have a Wawa employee has 4 shirts and 3 work pants. How many different outfits can he create? List them systematically. So there's lots of different ways to list out how many combinations you can create here. But I want you to notice these are from different sets. One is a pile of shirts, another is a pile of pants, and you're choosing one from each. So because you have 4 options for shirts and 3 for pants, you could just multiply 4 times 3, and so you would get 12 total options. And if you listed them all out, here's one way to do that systematically. I started with all the shirts and I called them shirt 1, shirt 2, shirt 3, or S1, S1, S2, S3, S4, and I put all the ones first. And then I matched each of the pants with that first shirt. And then I did the same thing, match each of the pants, the 3 pants, with the second shirt. Match each of the pants with the third shirt, and each of the pants with the 4th shirt. So you can see I did it systematically, going up, starting at 1, then going to 2, and then going to 3, and then going to 4. Now you could have done the same kind of system, but with pants instead, right? So you could have done, if I show you right here, so you could have done pants 1, and then because you have 4 shirts, you could list each of these with each of your shirts. Pants 1, shirt 2. Pants 1, shirt 3. Pants 1, shirt 4. And then you do the same thing with pants 2. And then you do the same thing with pants 3. And you would repeat all the shirts so that you would still get 12. So you can see there's different ways that you could list out these combinations. So these are called combinations. But either way, you get 12. And in this case, it's because the order doesn't matter. If you write shirts first or pants first, it doesn't matter because they're coming from different sets. So that's really important that there are 2 different piles of clothes here that you're choosing from. For example, if you were going to put 2 shirts on, now that's a different type of problem because you're choosing 2 shirts from one specific set. And then the order would matter. Like I put this red shirt on first and then I put this jacket on over it. If I put the jacket on first and then the red shirt on over it, that would be different and I would look odd. So in this case, these are different sets. You're choosing from different sets. Okay. So the next type of problem is all of the rest of the problems are choosing from the same set. And the difference is whether order matters and whether repetitions are allowed. So those are the 2 main questions. If you're taking elements from the same set, you need to answer those 2 questions. Okay, 3 dogs are competing for best in show. One must be chosen for first place, another for second place, and another for third. How many ways can the dogs be selected to win first, second, and third place? And let's list them systematically. So I named the dogs A, B, and C, and here I listed them systematically. So if dog A wins first place, then you can't select dog A again. So this is an example where repetitions are not allowed. So dog A can't win first, second, and third place. So dog A wins first place, and then dog B wins second, and dog C wins third. So that's one possible outcome for how those 3 dogs could win this competition. If I'm going to list them systematically, the next outcome should still start with A, so that I get all my A's first. The same way up here, I got all my shirt ones first. All right, so there's all the A's, then I listed all the B's, and then I listed all the C's. And I know that I'm done because I went through all 3 dogs, A, B, and C, and I just switched these 2 letters here, so then there's nothing else to switch. There's not a 4th letter. If there were 4, this would be a much harder problem because there would be a lot more in this list. So there are 6 total outcomes here for how these 3 dogs could win. You could also find this answer without listing the possibilities by asking yourself, how many options do you have for the first letter that you wrote? Well, you have 3 because you could have written A, B, or C. Now I started with A because I wanted to do it systematically. I didn't want to do it in a random way because then I wouldn't know if I got all of the outcomes. So systematically listing the elements is very important because it makes sure you got all of the outcomes. I didn't know that there were 6 before I started the list, but now I do because I'm very certain that I got all 6 outcomes. Okay, so we have 3 options for who could win first place. Once you pick that first place winner, now you only have 2 options for who could win second place. And once you pick both of these, like once I chose A and B to be my first and second place, I only had 1 option for the last letter that I could write, which is C. So you see that if you do it algebraically, 3 times 2 times 1 is 6. So you get 6 as well. So these are the 2 ways to do these kinds of problems. You could list out all of your options, which sometimes is not feasible because the answers are very big. Or you could do this spaces method where you write spaces and you fill in how many options did you have for the first space, how many options for the second, how many options for the third, etc. But you need to know how many spaces to write. In this case, I knew I had to write 3 spaces because we're choosing people for first, second, and third. Like if I was only choosing for first place and second place, then I would only have 2 spaces. All right. So here's another example. A company gives each employee a unique ID code made up of 3 letters, A, B, or C. If letters are allowed to repeat, how many unique codes exist? Okay, so now this is another permutation problem where repetitions are allowed. So that's different than the one we just did, which was a permutation problem, but repetitions were not allowed because the same dog couldn't win again. So these 2 problems, example 2 and 3, these are permutations because order matters. The order of the dogs winning matters because A, B, C that means A won first, B won second, and C won third. That's different than B, A, C. This shows B won first, and A won second, and C won third. So order clearly matters here. When you're talking about an ID badge, order matters here as well, right? If we all have ID badges, AAB would be different than BAA, right? So those are different. This is important because the next example that we're going to do in a few minutes, order does not matter, such as choosing toppings on your pizza. It doesn't matter if you say, I'd like a pizza with pepperoni and sausage, or a pizza with sausage and pepperoni. Now, it doesn't matter the order that you say it, you're still going to get the same pizza, because order doesn't matter in that case. Okay, so this is hopefully tying all of your knowledge together, where I said you have to ask yourself 2 questions. Does order matter, and is repetition allowed? All right, so here order matters, and repetition is allowed. So you can have things like AAA, and you can have AAB, and AAC. So notice I got all my A's there, everything starting with AA. And now here I've got all of my, I can't highlight just this, I have all of my ABs, and I'm just going through A, B, C for the last letter. Here I have all my ACs, and I'm just going through A, B, C for the last possible letter. Then I repeated the same exact thing, but starting with B first, and then the same exact thing starting with C first. So how do I know that I got all of them? Because I listed them systematically. So how many codes exist? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 3 is 27, so I could see it there. I could see 27. Or I could think about it using the spaces method. How many options did I have for the letter I could have written first? I had 3 because I could have started with A, B, or C. Now I did it systematically. I started with A. How many once I write, and when we do this spaces method, I'm just thinking about one possible element. Like, how could I write any element? Well, I'd have 3 choices for what letter I put first. I'd still have 3 choices for what letter I put second, because repetitions are allowed. And I've had 3 choices for what letter I put third. So 3 times 3 is 9, and 9 times 3 is 27. You can see this in the way I listed them here. I can see that if I were to highlight just these, let's see if I can do this. These are all my AAs, right? These all are AAs. Then these ones here are all ABs. And then the last set, these are all ACs. And so I can see my 3 groups of 3. I can see, oh, did I highlight it? I can see my 3 groups of 3 right there. So that's the first 3 times 3. And then I repeat this giant group 3 times. So that's my last times 3. So that's why we're using multiplication. You can see the multiplicative structure in the way that I listed it. Okay. So the next example is going to move us into thinking about combinations. So the last type of problem. So let's come back up here. So far we've done combinations created when choosing elements from different sets. That's like the Wawa shorts and pants. You're choosing from different bins. We did a permutation where repetition is allowed. That's what we just did with the ID badges. And we did a permutation where repetitions are not allowed. That's what we did with choosing dogs to win a competition. So again, permutations mean order matters. If it's your ID badge, it matters the order of the numbers or the letters. If it's winners of a race, it matters who wins first. The last type of problem is combinations, which mean order does not matter when choosing elements from the same set. Okay, these are the hardest types of problems, in my opinion. So we're going to go through these with 2 examples. Okay, so if 4 dogs are competing, how many different ways can winners be selected for first, second, and third prize? Okay, so I'm going to come up to the whiteboard. 4 dogs are competing, and you're choosing only 3. So let me make this bigger. I'll erase this. So 4 dogs are competing. You can call them whatever you want. I like to see letters for some reason. I like to see A, B, C, D. But you could use numbers too. You could use 1, 2, 3, 4 if you prefer to see numbers. So if I've got A, B, C, and D, and those are the dogs that I'm focused on, and I'm only going to pick 3. So now I have more elements to choose from, but I'm only going to choose 3. So that means all the elements in my set should only have 3 letters. So why don't you try this now? Why don't you try and list out what are all the possible ways that 3 out of those 4 dogs could win? Okay, so, and I already listed some of them in the file there, so you might have already seen it, but I think it's important to see how it's done manually as well. So the first way would be A, B, C, right? So I just went right in order. That should be all of our first possibility that we wrote. We should all have written A, B, C. Then we should try and get all the A's. Now, I don't know how many A's there are, so I'm going to do my best to do this in a systematic way. There's 2 different systematic ways that you could use. So some people will just switch these 2 letters right away and then start with 3 new letters with A. Other people do a kind of circular system where if you did A, B, C, the next option would be A, B, D, and you try and go in some kind of forward direction. So I'll do the first way I said. I will just, actually I'm going to do the second way because I like going in order and then coming back around. So we got A, B, C going forward like this. Another option would be A, B, D. So we skip the C, A, B, D. So I'm just gonna keep circling around forward. So now I got all my A, B's. So then I'm gonna skip the B now and jump to A, C, D. Okay, And I'm going to have to kind of circle back around and repeat this after skipping the B. So the next option would be A, C, B. Let me just show you what I did there. So I wanted to make sure I got all my A, B's and all my A, C's to start with. And so the first thing that I did was I did A, B, C. That was the easiest element to start with. And then I skipped over the C and did A, B, D. So that got all my A, B's, so I don't need to worry about A, B's anymore because I matched them with these two options already. So then I skipped the B, and I picked A, C, D. And then, because I still have to make sure that I get all of my A, C's, I circled this back around. So I'm doing A, C still. So here's my A and my C that I'm focused on. So I have to make sure that I match my A, C's with both of these letters. And the reason why I wrote the D first is because I like to go in this forward direction and then circle back around. You could have written the B first if you like to just go in alphabetical order. Okay. All right, so we're almost done with all of the A's. Again, because we're trying to do it systematically, the last couple A's that we need start with AD, because I did AB and then AC, so I know that there should be two ADs based on what the pattern shows up here. There's two of everything. And now when I'm done with this, I'll know I got all my A's because the last one is AD, and then there's no other option to start with A. So this has to be B and C, whichever way you want to write them. Now once you get all your A's, then you can write down all your B's, all your C's, and all your D's, and it should have the same kind of a pattern. So I'm going to pause my video and write them out, but you should be able to write them out as well. And I don't have to even write them out to know what the answer is. I know that there are 6 elements here, and if I'm going to do the same kind of thing for B, C, and D, then I'm going to have 4 groups of 6. So I already know that the answer should be 24. And then I'm going to show you how we could have figured that out without listing them. But I'm going to pause my video and list the rest of them out now. Okay, so I just wrote down all of the B's, all of the C's, and all of the D's. I started with BC, BC, then I did the BD, BD, BA, BA. Then here I did CD, CD, CA, CA, CB, CB. Again, I'm using this cycle of a pattern, so that's why I started with the CDs first, and then the CAs next, and then the CBs last. You don't have to do that. You can start with the CAs first, and the CBs next, and then the CDs. The point is you should have some kind of system where you could list out all of these options to make sure that you know that you've covered all of them. Now, we already know that the answer is 64, but another way to do this problem is with the spaces method. So we should get the same answer. You're choosing 3 things, right? Because every element that we wrote had 3 letters. So you should have 3 spaces if you're thinking about how many different options could I have here. How many different options did I have for the first dog? Well, I had 4 options. I could either choose A, B, C, or D to write that letter first. Obviously, I started with all the A's, but I had 4 options. Once you choose that first dog, how many options do you have for the second letter that you could have written in any of these sets? Now you have 3 left. So if you start with A, now you only have 3 choices left for the dog that can win next. And then once you pick first and second, now you only have 2 choices left for the final dog that could win third. If you multiply these out, you'll still see you get 4 times 6, which is 24. So either way, you get 24. Whether you list them out, whether you start the list and then see a pattern, see that you're going to repeat that 4 times, or whether you use this spaces method of asking yourself, how many options do you have here, how many options here, how many options here. You can see this 4 times 3 times 2 structure again. So here's the 4 groups, 1, 2, 3, 4. And then the 3 times 2 nature comes from seeing that I have 3 groups, each of 2 sets, AB, AC, AD. And every one of these lists has that same kind of structure, BCs, BDs, BAs, CDs, CAs, CBs. So you can see 3 groups of 2, and then 4 groups of that whole thing repeated. So you can see that this makes sense. Okay, So we're going to do, this again was another permutation problem where you are choosing dogs in order to win a race. The final problem, which to me is one of the hardest problems to wrap my mind around, is when order does not matter and you're still choosing from the same set. So in this example that we have over here, 4 dogs are available for adoption. How many ways can you select 3 dogs to adopt? I want to show you how can you select 3 dogs to adopt. I'm going to show you by using the set we just listed out. Okay, so we already know that this answer was 24. Give myself some room here. So now, if order doesn't matter, so this was a permutation that we just did, now we're going to do a combination. If order does not matter, you're choosing 3 dogs to adopt and take home for you, and you have 4 dogs to choose from. Do you agree order doesn't matter? You're choosing 3 dogs to take home with you. Does it matter if you say, I'd like a poodle, a pug, and a German Shepherd, or a German Shepherd, a poodle, and a pug? It doesn't matter the order that you say the dogs in anymore, because they're not winning a race. That means that if you choose A, B, and C as the dogs you want to adopt, this would be the same thing as B, C, and A. And it would be the same thing as C, A, and B. And it would be the same thing as a few others on there. Can you pause your video now and try and find all of the elements that would actually be the same if order doesn't matter? And let's only focus on the ABC set. So like, how many ABCs are there? How many groups of those 3 exact dogs are there if order doesn't matter? I'm going to search with you. Obviously, we'll circle that one. Yeah. So there won't be any in the last one, right? Because the last one has the dog D that you didn't select. So I see 6 total possibilities. Now, each of these should all have 6 total possibilities. And so I'll show you another option. If we find ABD, the group ABD, where are all the ABDs? Okay, 1, 2, 3, 4, 5, 6. So we got 6 again. And we could do another one. What about all the ACDs? ACD. This is still ACD, those 3 dogs. A, C, and D. A, C, and D. A, C, and D. And A, C, and D. And we got 6 again, 6 in orange. And then all of the BCDs, I will put in blue. BCD, BCD, BCD. All of those are all the same. So in other words, if you were to list out how many different options there are, if order doesn't matter anymore, then really you should only have 4 answers. And here are the 4 answers. You should have the group A, B, and C. You should have the group, I'll try and match the colors to how I circled them. A, B, D. You should have the group, so let's see, what, orange? Let's get orange. A, C, D, and then in blue. So here's A, C, D. And then the last color that I circled all in blue are B, C, D. Now, you could have answered this question if you listed them out systematically. You could have looked at your list of these 4 possible choices for dogs. And if order doesn't matter, then you could have listed A, B, C would be my first option, then A, B, D would be my next option. Now I got everything with A, B's. And then I would skip to the A, C, D. And now I have everything with my C's because I already got this option with my C since order doesn't matter anymore. And then the final one would be B, C, D, and then I'm done because I have everything now that you could have had with B, C, and D. I'm going to show you how to calculate this. So the reason why we did all this work, you're probably wondering, like, why don't we just write that out and then know that the answer is 4? Because to write down the method for finding out these answers algebraically, it's easier if you see what's happening here and why the answer is 4 if you do it this way, or it's 4 if you just list them out. Okay, so the total number of elements here for the permutation was 4 times 3 times 2, which was 24. The answer for the same problem, but as a combination where order doesn't matter anymore, should be less. You should have less options if the order that you say them in doesn't matter, because some of these elements are the same if order doesn't matter anymore, like all the ones in pink. How many of them are the same? In this case, 6. 6 were the same. So if you divided this by 6, then you would get 4. You would get the correct answer. How do I know that there's going to be 6 duplicates? In every single case, in every single one of these elements, there will be 6 of the same group. How do I know that? Because if I just take one of these groups, it doesn't matter which one, I already know that there are 6 different ways to put these letters in order, right? How many different ways can I put these letters in order? Well, I could do A, C, D, or I could do A, D, C, or I could do C, A, D, or I could do C, D, A, or I could do, starting with the D, D, A, C, or D, C, A. So I already knew how to put those things in order. And we actually just did an example of this where we saw if you have 3 dogs, like A, C, and D, and you're going to put them in order to win first, second, and third place, we already knew the answer was 6. And how did we get it? Because how many options do I have for the first letter I could have written? 3. How many options do I have for the second letter once I choose the first letter? 2. And how many options for the last letter? 1, once I choose the first 2. So we already know that there should have been 6 copies of every single option when order doesn't matter any longer. So these are all the 6 same groups when order matters. So we're going to divide by that so that we only count this group once. So if there's 6 here, but I only want to count it once, then I'm just going to divide by 6 because each one of these options has 6 duplicates. And we don't want to count them because they're all the same group. Okay, so that was a lot. So the general formula for how to find the number of combinations when you're choosing from the same set is you figure out how many things you're selecting. In this case, we were selecting 3 things, and we had 4 options. So you would have something multiplying on top 3 times, and then dividing by however many things you have up there. You would be doing, in this case, if you have 3 things, you would be dividing by 3 times 2 times 1. If you had 4 things on top, like let's say you wanted to select 4 dogs, then on the denominator you would divide by 4 times 3 times 2 times 1 because you're ordering 4 things and you're removing all of the duplicates of those 4 things. Now, the answer that goes up here depends on how many things you have available to select from. So like if you have 10 dogs to select from and you just want to take 4 home to adopt, then up here this would be 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. Okay, so practice problems will help a lot to understand this concept. I'm going to give you 2 pieces of notation. So one is called a factorial. This 4 times 3 times 2 times 1, that is the same thing as 4 factorial. So anytime you see an exclamation mark in math, it means start with that number and multiply down until you get to 1. So this 10 times 9 times 8 times 7, that's not the same thing as 10 factorial because it doesn't go down all the way to 1. So this goes down all the way to 1. And then the other thing that I told you was if you already know how to do permutation and combination problems, then you could use your calculator. I'm not going to explain it though, so you'd have to already know this. So if you don't know it, then don't use that method. Just use this method here, this spaces method, and then you should be dividing when it's a combination problem from the same set. And you should just be multiplying for all the other types of problems. Any permutation problem is just multiplication. Any combination from different sets is just multiplication. But if you remember this, any permutation problem you can use in the calculator NPR, where you have n total things and you're taking r of them, like 4 dogs and you're selecting only 3 to win a race. Or you could use NCR for combination problems where you have 4 dogs and you're going to only adopt 3. So in this case, n is the total, r is the number of things you are selecting. Okay, again, this was a lot. So if you have any questions or you want to go over any of this material one-on-one, then just contact me and I'm happy to help.